All right, let's see how you did on this first question where we are rewriting a formula in terms of some slightly different variable than what is usual. On number one, write a formula for the area of a square in terms of its perimeter. Okay, so I want to start with what it asked me to write, which is a formula for the area of a square. The traditional area of a square formula is just side squared, which is in terms of its side length. You need to know the side length in order to calculate the area of that square in terms of S. But we want to rewrite it so that it is in terms of P, perimeter. And what that means is that our equation, our final answer, is going to look like A is equal to stuff, and that stuff contains only the variable P. It can have other numbers and stuff in there, other constant values, but the only variable that's on that side is P. That tells you that you need to come up with an equation for P that has an S in it. Well, that's the only formula that there is, which is handy. Our P is equal to 4S. Now you want to take a look at both of your equations and identify what they have in common. Here we have an S in common, an S, a side length on both of the equations. That shows you which variable that you're going to solve for. And you're not going to solve for the S and the A equation. Why is that? The reason why is because it tells us to write a formula for the area of a square. I need to leave my formula as A equals stuff. So it stays put, and I'm going to solve the perimeter formula for S. The 4 is being multiplied times S, so I'm going to divide it over to the other side. So I have S is equal to P over 4. Now I'm going to take this P over 4 and just substitute it into S in the original area formula, which will look like this. A is equal to, think of S as a placeholder and put P over 4 in its place, and then square it. And then once again, this is an acceptable answer. You don't really have to do anything to it unless you feel like you want to simplify, or you're trying to simplify to make it match up with a multiple choice answer choice. If I were going to simplify it, I just need to square the fraction. I need to square the top separately from the bottom, and I would have A is equal to P squared over 16. So now we have a formula for the area of a square in terms of its perimeter. That just means that perimeter is what you need to know in order to calculate the area. It is the independent variable. You could take the perimeter of a square and you can square it and divide it by 16, and that would give you the quantity, the area. Okay, all right, let's look at number 2 because this one's weird. Show that the perimeter of a rectangle can be written as, and we have the strange formula, P is equal to 2A plus 2W squared, all divided by W. So when it says show like this, your answer is your work. It's not like over here where your answer is this new formula that you got. Your answer in this case is the work that is going to basically prove that this could give you the perimeter of a rectangle. And you can do this in a couple of different ways. The easiest way, I would say, is to start with the equation that we have right here, do some algebra on it to show that it looks like the traditional perimeter formula. All right, so can we make this thing look like 2L plus 2W? That's what we want to try to do. Okay, so to make that thing happen, I have this A in here. Sure, we already have a W. This is a fraction. We'll figure that out in a minute, but there shouldn't be an A in here. This A is, of course, the area. And how do you calculate the area of a rectangle? That formula is length times width. And now, just like before, if you notice, These two equations now have an a in common. So if I solve this one for a, which it's already done, I can use this L plus W. I could substitute the L plus W in the place of where the a was. So this becomes, after substitution, 2 times LW. And since this is all multiplication, you really don't need the little parentheses that are right there, of course, plus 2W squared, all of this over W. Now, just to make this really clear, I am going to write this as two separate fractions. It's the distributive property. You have to distribute through division. You got to divide W into both the first term and the second term. So it would look like this. 2LW over W plus 2W squared over W. And then you can divide. You can divide these W's. You can divide one factor of W on the bottom of the second term with that squared here, because remember, that's really W times W, and one of them goes away. And then look what you're left with. You're left with P is equal to the traditional 2L plus 2W. And you got it. And again, your answer is not this. Your answer is the work that you did in order to get there. That's what it means to show. Okay. But let's say that I did it sort of like what we did over here in question 1 and the other sample problem that we did right up here. And that is, let's start with the traditional perimeter formula, and we just have a goal in mind. We need to rewrite it in terms of not just A, this has two different variables on this side, so it's in terms of A and W. If I look at the perimeter equation, which is a raised to P for some reason, it's in terms of length and width. We need to get rid of the L because that's the thing that's not in here. And we have to replace it with some equivalent expression that has A in it. Okay? All right, so let me add an extra little page here because this is going to take some space. All right, so I'm going to write all those things down, pretending I didn't know what the answer was. I have 2L plus 2W, okay? And again, this is in terms of L and W. We want it in terms of A and W. Sounds like a root beer. Anyway, so I need a formula for A that has a W in it and an L in it, which is the only one that exists. I guess you could do it in terms of base and height, but then that would be totally confusing. Okay, so what variables do these things have in common? They have an L in common, but then you could also say that they have a W in common. But the issue is that we want to keep the W, right? The answer that we're aiming for has a W in it. So I'm going to get rid of these greens here, ignore that, and I want to replace this W. The perimeter equation needs to stay as it is, which means that we need to solve this A formula for L. L is being multiplied times W, so I'm going to divide it over to the other side. So that would look like this. I would have A over W is equal to L. Okay, so now I'm going to take A over W and I'm going to substitute it in the place of L in the original perimeter equation and then see where that takes me. P is equal to 2 times A over W, and then bring down your 2W. All right, so far, this right here does not look like the answer that they gave us because there's a W squared here, and the whole thing is written as a fraction. Okay, so I'm wondering if there's more stuff that we can do to it. Now, as we saw before in another exercise, I'm multiplying a 2 whole number times a fraction here. So where does this 2 go? Remember, this 2 is essentially 2 over 1. When you multiply straight across, the 2 is just going to go up top. And then the W will stay on the bottom. Okay, so maybe simplifying this fraction, I'd have 2A over W plus 2W. Okay, so now we want one complete fraction. If you have a fraction and something that's not a fraction, in order to combine those two things, you have to have a common denominator. And you only have one denominator, which is w. So if I get this one to have a w on the bottom, then I would have a common denominator. Not the only way to do this, I'll show you another way in just a second, but let's rewrite this term so that it has a w on the bottom. And the way that I do that is with a fancy one, which is w over w. Right, you do this numerically whenever you're adding fractions. Say that I wanted to add 7 to the number, I don't know, say 1/4. Since this one doesn't have a 4 in it, you multiply it by the fancy one, 4 over 4, to make this thing 28 over 4 plus 1/4, so that you can add these two fractions. You would add the top and keep the denominators the same. And that is essentially what I just did here, except for with variables. Okay, so my new equation is P is equal to 2a over w plus, now, once again, I have a non-fraction multiplied times a fraction, and it's top times top and bottom times bottom like that, and I would be left with 2w squared, there it is, over w. And then one last thing is, whenever you combine these two fractions, you add up the tops and keep the denominators the same. For example, over here on this example I just showed you with numbers, I would add the two tops here to get 29, and then I would keep the bottom as a 4. I'm going to do the same thing over here. Add the two tops, since they're not like terms, they're not going to combine, and then keep the denominator as a w. So P is equal to 2a plus 2w squared, all of this over w, and now that exactly matches the answer that was given. Okay, so let me show you back up here on this stage another way to have done it. So I'm just going to bring that equation down one more time. Let's do this in green so you can see an alternative method. P is equal to 2a over w plus 2w. Okay, so this is an equation that has a fraction in it. And remember, one of the strategies when you're dealing with equations that have fractions is that you can multiply by a common denominator and you can get rid of them. So if we multiply everything by a w, it's going to get rid of the w on the bottom of this fraction right here. So multiply everything by w. P times w. Whoa, I switched to blue. There we go, is equal to this 2a times w. The w's are going to cancel the one on the bottom, and this w that I'm multiplying it by is going to cancel, leaving me with just 2a. And then I multiply this 2w times w, and w times w is w squared. Okay, and then we wanted to solve this thing for p, so p is by itself. P is being multiplied times w, so you can just divide this w over, and that would be P is equal to 2a plus 2w squared over w, which of course matches up with this one. It's pretty crazy, right? And you could see, obviously, this initial method that we did right here with that first substitution of length times width in for area, that was much faster. But that assumes that you knew what you were aiming for here, that you were given the answer. Okay, one last one. Let's take a look at this one. Write a formula for the area of a right triangle in terms of its base b and hypotenuse c. So this is in terms of two different variables. We've got base and hypotenuse. So as a triangle, its area formula is the same of any one, which is 1/2 base times height. Okay, and now remember that the base and the height here always have to make a right angle, which means that this segment over here on the right-hand side, since it makes a right angle with the base, must be the height. I'm going to just label that with an H. Okay, this one, the area formula for a triangle is right now in terms of base and height, but I don't want height, I want C in here instead. So I need another equation that's going to relate these variables together So I can get something to substitute h away. We want to get rid of it. All right, it's a right triangle. What is an equation that relates the side lengths of any right triangle? That is the good old Pythagorean theorem. So the Pythagorean theorem for this triangle would be something like c squared is equal to, we know it's a squared plus b squared, but our a is essentially this h that's right here, h squared plus b squared. All right, now, what is it that these two equations have in common? I'm going to highlight them. They have an h in common, but they also have the b in common. Oops. But b is something that we wanted to stick around, so we're going to ignore it, and we are going to get rid of the h. That tells us that we have to solve this Pythagorean theorem for h. We're not going to solve the area formula for h because the question asks us to write a formula for the area of the right triangle. So it stays. Okay, so then how do I get h by itself? H is trapped inside of a square. So should I just take the square root? I'm gonna, but you have to get the h squared by itself first before you can take the square root. I have to get rid of the b squared first. B squared is being added to the h squared, so I'm going to subtract it over to the other side. So my equation is going to become c squared minus b squared is equal to h squared. Now I can take the square root of both sides because I have my squared term, my quadratic term, isolated. So I'm going to take the square root of both sides, like this. Okay. On the right-hand side, as we talked about, the square root and the square will cancel out, leaving me with just h. And the question that most students have is, well, doesn't it do the same thing over here on the right-hand side? We have squares. We have square roots. Will they cancel each other out, giving me just c minus h? And the answer is no. The reason why it's not is because squares and square roots are inverses of each other, but the difference between two squares and square roots are not. There's an extra operation in between there, so it sticks around. So I would say, don't simplify it here, just write down what you have like this. Okay, let me show you this with numbers, just so that you can see, you can verify that that makes sense, that you can't cancel out the square root and the squares in this case. So I'm going to use the regular Pythagorean theorem with a squared plus b squared equals c squared. And what I'm going to do, c squared, is select some numbers that we know work in the place of a, b, and c as whole numbers, something that's super easy to work with, and you're probably familiar with this. It's called a Pythagorean triple, and the simplest one is 3, 4, 5. So 3 squared is 9, plus 4 squared is 16. You add 9 and 16, you get 25, which is 5 squared. So 3, 4, 5, that is, like I said, a Pythagorean triple, 3, 4, 5. It works as the side lengths of a right triangle. Okay, so let's do what I just did right up here. Let's solve it for one of these over here on the left-hand side. How about we solve it for 3? Okay, without squaring yet, let's just solve it for 3. I'm going to subtract over the 4 squared. I'd have 3 squared is equal to 5 squared minus 4 squared. Okay, and now let's take the square root of both sides, just like I did to simplify this equation. Take the square root of both sides. On the left-hand side, when I take the square root, stop moving. If I take the square root of 3 squared, those cancel out as inverses since 3 is positive. So 3 is equal to, and then let's see. Let's say that I thought that the same thing happens on the right side, that these squares and the square root cancels out. Watch what happens. I get the crazy formula that 3 is equal to 5 minus 4, which means that 3 is equal to 1, which most of the time is absolutely not true. But if we follow our order of operations back up here on this stage, and I square first, I would get 25 minus 16. Okay, and then this is essentially something that's inside of a square root, so I have to do it first. So I'm going to combine the 25 and the 16. I have to subtract those two things. That's the square root of 9. And then the square root of 9 is the 3 that we would have gotten on the other side. Okay, all of that just to show you, just to demonstrate with some numbers, these don't cancel. Oh, hey, dot that. Just gave it pimples. Okay, anyway, so these things don't cancel. I'm going to leave it like that. Whew! Now, for substitution, I'm going to take this whole guy right there, and I am going to substitute it in for h in the area formula. To rewrite my area in terms of the base and the hypotenuse, it goes like this. 1/2, this b can stay. It can stay because the original problem says that base is one of the independents. Take out the h, replace it with c squared minus b squared. There you have it, folks. The area of a right triangle in terms of just its base and its hypotenuse.